So, to continue talking about one-dimensional kinematics, and more specifically, velocity, and also doing some of the calculations within looking at some more graphing as well. So, last time we talked, we had kind of finding the slope of this line. And at the end, I mentioned finding the instantaneous velocity of different points. Finding the instantaneous velocity at 2 would be finding the slope of the red line. Now, the reason why that is the instantaneous velocity is because we have a position at an instant in time. It doesn't help us kind of the whole, it's noon, how fast am I going? You don't know, right? You need to know more. Okay? When it comes to finding that instantaneous velocity, you need a time interval to help us out. The fact that I'm in Mankato at noon doesn't mean anything. Okay? Having more information, how fast was I going before noon and then maybe just a little bit after noon, say 11:59, noon 01, gives me a time interval. Where is my position at those two times? Then that would give me a distance, or at least a spot that I would be able to adhere to, a displacement, and therefore I could find the change in my displacement to determine what my instantaneous velocity is. Just giving me a time and a location doesn't help us. So the limit equation has us looking at the displacement over a time interval again. But a limit equation tells us, has some extra information. For those of you that have not taken calculus, that's fine. All you really truly need to know with a limit equation is that this bottom part here is just trying to indicate that the time interval needs to become smaller and smaller and smaller. What we're saying with the delta t approaches 0, meaning the time interval needs to approach 0. Now, we can't technically have the time interval be 0 because if I have a displacement divided by 0, I don't have anything going on. Okay? So the time interval just needs to be really, really small. As small as the technology allows. Sometimes the time interval, the best that we could do might be seconds, but then it might be hundredths of a second in another instance. So we need to be very careful. Why is instantaneous velocity important to look at? Because again, you can have an average velocity, which sometimes is just kind of looked at as the average speed that the person takes. The lower graph indicates kind of a speed up And then, whoa, slow down, going a little fast. The average velocity is the dotted line here. The instantaneous velocity looks different. In a position time graph, because that's what this is, because it has the curvature, to find the instantaneous velocity there, we take the slope at a given instant. Now, when we look at the graph, we know it's speeding up because it's quadratic in nature. It's curved. And those of you that have taken calculus might be able to determine points on there differently. However, those of us that have not taken calculus, we can use algebra. We just have to find that time interval. And therefore, that time interval, the run, will equate out to a distance interval as well, the rise, and therefore allow us to solve for that instantaneous velocity. It just might take more work. So, if I have the block or the little wheel cart moving down the ramp, total distance of the ramp is 2 meters. Time it takes is 3 seconds. Quick and easy math. 2 divided by 3, 0.67. Somewhere in your notes, it might not be a bad idea to try to guess, where does the actually instantaneous equal the average? Is it somewhere in the B bracket? Is it at A? Or is it somewhere in the C bracket? Guess. As we continue through, kind of let it be known. Okay. So, how much do you move your pencil when you see a graph like this? Not very much, do you? So the position of your pencil doesn't move. So the position of the object also isn't moving. How about this one? Well, if you took the slope of that previous line, what would it be? There's no rise. 0. So the velocity time, also 0. The slope of the line, the slope of a distance time graph gives you the slope that you should use for a velocity time graph. Why? Again, velocity is equal to change in x divided by change in t, which, as we've said before, is the rise over the run. So if the slope is 0, that's what you have here. Now, we'll talk about this maybe Thursday, maybe Friday. Probably not Friday, but Thursday at most, at the earliest. There is going to be an additional graph as well with that. How about this one? This one has a slope of some sort, right? Okay. Now, what usually most students don't like is the fact that there's no numbers, right? Can we say that the slope would be positive or negative? The slope would be positive. So when we correspond that to the other one, it doesn't really matter where on the velocity time graph we put it. It's just that it has to be on which side? Positive side. That's it. Just has to be on the positive side. How about something like this? This indicates speeding up, as something rolling down a ramp would do. Especially if it started from rest. Here, it's going to have some different things going on. How do we calculate that? Well, we kind of hinted at that last time. Well, we're going to figure that one out. So here we said the slope would be 0. Here we said the slope would be positive. Now for here, at t equals 0, slope would be 0. Whereas as far as we can see, as best that we can see, that line right there didn't correspond out very well, or transfer. But the slope would be about 0. So we graph that, 0, 0. At about 1, we have a little bit different. Okay? Now we have a rise. Change the color here. We have a rise and a run. So we have some slope, right? Positive as it may be. So we put that position in there. At 2, better line, transfer it over. Somewhere it's got to be around 4, I'm guessing. Hey, looky there. Can we guess what this velocity time graph is going to look like? Yeah, we're gonna. Usually after you get that third point and you're like, okay, I got it. And then at 3 seconds, guessing somewhere around 8. No, it was wrong. 6. Now, if it's direct, I guess I should know better. It looks like it's by 2. And at 4, should be around position of 8, or 8 meters per second, because that would be the velocity side. And therefore, we're going to have this nice direct line. Now, bringing back the idea of that previous slide, the average velocity of the object as it goes down the ramp, does it happen at the beginning, right in the middle, or at the end? Is it going to hit its average velocity right in the middle, which a lot of students are going to think. Why would we think, hinting that that's not the answer, right? Why would we think the middle is the correct answer?
If the acceleration was linear, it would be.
If the acceleration were linear, it would be. And therefore, but that's not how it works. It's quadratic, right? It's speeding up. So is it going to hit its average velocity in the beginning or at the end? Think about it. Because more time has taken place at the beginning, the average is actually going to be achieved in the first third or so of the ramp as it goes down the ramp. The middle, we guess that it would be because, oh, it's in the middle, average is in the middle. But that's not how physics works. It's going faster, covering more distance in a smaller time interval, because that's how ratios work, right? Because a ratio is going to work, especially for these. Ratio is going to work a change. Oh, if you're going to write these things out right, it would make sense if you read them in the right order, right? Change in x over change in t. If it's going fast, say just a simple 1, 2 over 1, right? But what happens if it didn't cover as much and it took longer? It's not going as fast. Okay? Think about driving a car. Okay? When they up the speed limit, it means it takes you more or less time to get to where you're supposed to be going. Less time. Because that is allowed to be going higher. The distance that you're going to travel is going to be constant, right? Especially if you're like going to like Mankato or Jordan, right? The distance is constant, right? The distance between 2 points is still there, right? So the only thing that can go up or down is your time. If this is going up, if your velocity goes up, your time has to shrink with that.